All right, everybody. Hello and welcome back. Today, what we're going to do is we're going to take a look at some applications for exponential functions. So this is the equation we've been dealing with so far, specifically when we've been trying to determine what our growth or decay rate is. We have this equation where A is going to be our end amount, P is our principal balance, or starting amount. Our R value is our rate, and then T is going to be our time. So as we mentioned before, it's very similar to the problems before. We were trying to determine what our growth or decay rate is. Now, the P is our starting value. 1 represents our initial amount, and either we are subtracting from it, and it will be a decay example, or we are adding to it, and it will be growth. Now, what we really did is we changed our x value to t simply because what's going to affect these problems, particularly when we're talking about interest, is the amount of time that your money is in your account. So again, this is really just the same formula we've dealt with before. Let's say a bank account has $4,000 in it and is increasing at 2%. Well, we could just plug in our rate, plug in our p value, our principal amount, and then figure out after how much time how much money we'll end up with. Now, some accounts in particular have this rate value spread out over several different intervals. And what that means is the interest is compounding. So essentially how that works is they'll take a little bit of that rate and they'll apply it at one point. So your balance will grow. And then a little bit later on, they'll apply a little bit more of the rate. So the balance will grow even larger and then more and more and more. So when you have compounding interest, that's basically something we would want in an account because you are earning interest on interest. You are earning money from money you have been given. Now, what that would look like is basically the same equation, except we're going to have to divide this rate value by however many times we are going to compound our interest. And therefore, we're also going to have to change our exponent to not just time, but the number of times that our rate is being compounded. So this is our compound interest formula. Again, very similar. Everything is almost exactly the same. We've got our initial amount, our principal value, or principal amount. Our R is our rate, T is time, but now our N value is going to be the number of times interest is compounded. So it's a very slight difference. Again, we just divide that rate by the number of times we're going to compound the interest, and we're also going to have to affect our exponent, and we're going to change it by multiplying time by the number of times that is going to be compounded. Now, we could talk about a few examples, and we'll look at one in its entirety below here. But what happens is we want accounts that compound interest more often. So for example, some accounts do it every 6 months. Some accounts compound interest every month, every week, or bi-weekly, or daily. But what starts to happen is as our values down in the in the denominator here, start to increase, this entire value starts to approach a specific number. And essentially the idea there is interest can only increase so fast. And what those values start to approach, and you could plug in different numbers to kind of see what ends up happening. What I mean by that is if we're looking for the end amount, we started with $4,000 like before. Our interest rate is 2%. Let's say we compounded interest 4 times. So we plug in a 4, and then we'd have whatever our t is, let's say 5 years. Well, as this value in the bottom here, our n value starts to increase, so such as if we were to compound interest every month, or if we were to compound interest every day, we can even go from there. We could do every second, we could do every minute, but essentially the idea is this part of our equation starts to approach a number that is about 2.71 so on and so forth. Now, that number is a special number in math. It is called the natural number e. So our equation shifts a little bit. So we have still our this is our end amount. Which means I wrote the wrong thing here. Sorry about that. This is our end amount, how much we end up with. This is our principal amount, or the amount we start off with. T is time, R is rate, and E is a number. It's not a variable like our other values here. It is approximately 2.71, I believe it's 8 something something something, but that value is going to essentially signify that we have continuously compounded interest. And what that means is every second, every fraction of a second, every possible moment, our accounts are gaining interest. And now students typically see this value E and they get very thrown off, but E is just like any other number. And what that means is we can graph the function f of x equals e to the x power. And it's going to be just like we would if we were graphing 2 to the x power. We pick some nice x values that we want to plug in. And again, when we're graphing exponentials, we should always go with 0 and 1 because those are the easiest. And we plug into our equation like we would normally do. We end up with e to the 0 power. Well, anything to the 0 power is 1. And then we have e to the first power, which is just e. And again, e, if you want to type into your calculator, and we can do that just to see what it looks like. We get 2.718281828446, and it actually goes on and on forever because it is an irrational number. Think about the number pi. It's a symbol, but it means something. There's a specific value that it holds. Now, if we were to type in any other letter, we don't get those same values out. Nothing comes up because E is special. E is its own number. E is approximately 2.72. So if I just estimate 2.72 here, we can actually graph e to the x power. So we've got -1, 0, and 1, and then we can do 1, 2, and 3. So I'm just going to quickly graph this just to, again, show you that e can be treated like every other number we are comfortable with, every other number we are familiar with. It is a value and not a variable. So if I plug in these points, we've got 0, 1, and then we've got 1 comma e, or about 2.72. So this exponential function is going to look just like this, which is just like the exponential functions that we graphed before. We can even do operations on these values. And again, we treat it like every other number. In this case, if we were to simplify the expression, we would multiply our numbers. 2 and 4 is 8. And then when we have two values and their bases are the same, we take their exponents and we are going to add. So this expression simplifies to 8 times e to the 5th power. Similarly, we could do a problem like this where we are doing division. So I threw a variable in here to go along with our numbers in e just so we could see that they are treated exactly the same. So we simplify our numbers. 3 over 6 is going to simplify to 1 over 3. And then when we've got values in our numerator and denominator, we are going to subtract their exponents. So there are more x's in the numerator, so that means x is going to stay in the numerator. And then we'll have an exponent of 2 minus 1, or 1. E is going to be treated the exact same way. We've got a value with we have exponentials with the base value that is the same. So we're going to subtract their exponents. Now, there are more e's in the denominator. So that means e is going to stay in the denominator, and we will have 4 minus 2, or 2, as our exponent. So my whole point here is what we are really trying to focus on is the fact that although e looks strange, it's really just like any other number to us. And e, in this case, in this application, represents continuous compounded interest. So here's a problem that kind of summarizes our new ideas here. It says you're interested in opening a savings account. Before doing so, you research 3 different accounts at your local bank. Account 1 offers 2.3% compounded once annually. Account 2 offers 2.32% compounded monthly, and then account 3 offers 2.25% compounded continuously. Which account is the best offer? So let's say that we are putting in an initial amount of $5,000, and we are just going to do it for about 5 years. So we've got our three accounts. One is a 2.3% interest compounded once annually. So in that case, we're going to use our original equation right here. And if you think about it, it's really this equation as well, except the difference is here in our specific example, since we are only compounding once annually, our n value is 1, which makes these two equations the same. So we have a equals p times 1 plus or minus, but since we are increasing because of our interest, it's going to be plus our rate to the t power. A equals our principal amount, which I think we said was 5,000, times 1 plus our rate. Remember, convert that rate from a percentage to a decimal. So it'll be 0.023 to the 5th power because it's going to be in the account for 5 years. And now I'm going to do this on my calculator on the side here just to make things easier for us. So we have $5,000 times 1 plus 0.023 to the 5th power. That leaves us with an end amount of $5,602 and about 7 cents. And because it's dollars, we're going to round to 2 decimal places and add our dollar symbol. Now, our second account is different because we are going to compound interest at a different rate, and we're also going to do so monthly. What that means is we're going to take a little bit of that 2.32% every single month. And so our interest will grow and grow and grow and grow. So in this case, our interest rate is a little bit more, and we are compounding more often, which means we should end up with more money. So we have A equals P times 1 plus R over N to the N times T power. Well, we're looking for the end amount. My principal, we said, was 5,000. 1 plus my rate, this rate is 0.0232, divided by the number of months, the number of times we're going to compound. In this case, it is monthly. That means 12 times in 1 year. So our n value is 12. So again, I'm going to type this into my calculator. We have 5,000 times 1 plus 0.0232 divided by 12 to the 12 times 5, or 60th power, is going to give us $5,614 and approximately 35 cents. So of these two accounts, I'm rolling with account 2. Again, a slightly higher interest rate, and our interest is going to compound or be taken at different points in time, which means we earn more of it. Now, our last account has an interest rate of 2.25%, but is compounded continuously. That is more than every second. That means we are always earning interest. So in this case, we're going to use what is sometimes referred to as our PERT formula, P-E-R-T. So I'm going to go ahead and start plugging in. A equals P times E to the RT power. Principal amount, as we said, was $5,000. My E value, remember, E is a number. It is 2.72 approximately, so we're just going to leave it as E. We don't need to plug in 2.72 because that's us rounding, which isn't the actual value. So we want to keep it as E. We'll plug in our rate, which was 0.025225 times 5. So this account has actually the lowest interest rate, but compounds the most often. So we're going to kind of see, hey, maybe this is a better choice. We don't really know yet. Just because our interest rate is lower does not mean it's a worse choice because of how often our interest is compounding. So I'll plug this in my calculator. We have 5,000 times E to the 0.0225 times 5 power, and we are going to end up with $5,595 and approximately 36 cents. So the account we're going to want to roll with is going to be account 2. account 2 here, and I'll highlight it in our writing, gives us the best value. And so there are a couple things that we want to keep in mind. Our equations are very similar. This equation is essentially this equation, but when the n value is 1. So students tend to think of these as two separate things, but really they're not. This is one equation, and in this case, our n value was just 1. So our first account had the second highest interest rate, but only compounded once annually. So we plugged it in, and after 5 years, our $5,000 becomes $5,602.07. Now, account 2 has a slightly higher interest rate, which is good, right? We want more interest, and that interest is taken more often. So we are earning money on our interest. When we plug that in, after 5 years, our account grows to $5,614.35. Lastly, we have our account 3, which is 2.25% compounded continuously. So the compounded continuously is awesome. It's great. We are always earning interest, but our interest rate is a little bit lower. And as we found out at the end, that lower interest rate isn't going to give us the value that we want. It's not going to give us the most amount of money, which is ultimately our goal, even though it is compounding continuously. So these are our compound interest formulas. Again, they're written up top. We have our PERT equation, which we use whenever we see the word continuous. It is for continuous interest. And then we have our compound interest formula, which is, in this case, essentially the same as this equation with an n value of 1. As always, thank you for listening. If you have any questions, please feel free to reach out. Thank you.